Hello everyone, welcome to this video. In this video, we'll be looking at various examples illustrating the fundamental theorem of group homomorphism. So we can consider a mapping phi from the group D4 to the same group D4. You know what is D4? It is a dihedral group consisting of these 8 elements within it. Right now we say this mapping phi is a homomorphism. You can verify this by taking any 2 elements out of it, right? And if this is equal to phi of x phi is equal to phi of x phi of y, then you have the operation preserving property within it. And if you have the operation preserving property, you have the homomorphism, right? So we say it is a homomorphism. You can check this property by yourself here, correct? So now, because this is a homomorphism, we can apply the fundamental theorem of group homomorphism. So according to the theorem, we would have some mapping psi from where to where? From D4 by the kernel of this mapping phi to where? To the image of D4 under phi, correct? So we would have an psi as an isomorphism. So we first of all define this homomorphism by defining like this, that such that phi of R0 goes to R0, phi of R180 also goes to R0, right? Phi of R90 goes to H, phi of R270 also goes to H. Similarly, phi of H goes to R180, phi of V goes to R180, correct? Phi of D goes to V, and phi of D dash goes to V again, right? So we have this mapping which give us homomorphism, right? Now what is the kernel of the mapping? You know, in D4 what is the identity element? The identity element we have with us is R0. So the only elements which are mapping to R0, they are R0 and R180. Hence, they both become the member of your kernel phi, correct? Now, you know what is your kernel phi. Therefore, now you can very easily define this mapping psi. The mapping psi would, as I have told you, would take the elements of D4 oblique the kernel of phi, right? This factor group to the image of D4. And what all elements are present in the image of D4? You can clearly see we have R0, H, R180 and V present in the image of phi, correct? So we have 4 elements present here within the image. And in the domain, what elements do we have? We would have all the what? Cosets of this group D4, correct? So the cosets are constructed by taking any elements and looking at the distinct, so you see we only have 4 distinct cosets here. One is R0 kernel phi, another one is R90 kernel phi, because R0 kernel phi contain both R0 and R180, and this would be further equal to R180 kernel phi, so we are leaving this thing. Similarly, we have R90 kernel phi, which is R90, R270, which is equal to, if you notice and look at it, it would be equal to R270 into kernel phi. Similarly, H kernel phi also contain 2 elements, and D kernel phi also contain 2 elements within it, right? And they further would be equal to V kernel phi, and this would further would be equal to D dash kernel phi, correct? So we can now define the mapping psi in this manner that phi takes R0 kernel phi to R0, it takes R90 kernel phi to H, it takes H kernel phi to R180 and D kernel phi to V. Now we say this mapping is an isomorphism by the fundamental theorem of group homomorphism. You can check that this mapping is well defined. This is 1 1, this is on 2, and obviously it is operation preserving as well, right? So therefore this is a homomorphism. Now let's move on to our second example here. In this case, we consider the mapping phi from the group of integers to the group of integers under modulo n, right? We have already discussed about this mapping. We define this mapping by taking any integer m, and when you apply phi onto it, you apply mod n onto the number m, correct? This is how we define it. Now we say this mapping is a homomorphism. Why? Because we already have proof. If we take two elements m and p, right, this would give you equal to actually here what is the group operation? It is addition. So phi of m plus p would give you phi of m plus phi of p, correct? So you can check that this relation is there. The kernel of this mapping is given by this cyclic subgroup, which is generated by small n, correct? Where what is this n? This is the index of this Zn. So by the fundamental theorem of homomorphism, we can very easily define the mapping psi taken from this group Z, the factor group of this group, right? So this factor group is obtained by taking the kernel of phi to this Zn, which is the group of integers under modulo n. We say this is an isomorphism. If this is an isomorphism, that means these two groups, this factor group and the group of integers under modulo n, they both are isomorphic to each other, right? So you see how simple it becomes equal to. So that means the structure of this factor group and this integer modulo n group, that is the same, because we have an isomorphism between them, correct? So this isomorphism is obtained from this mapping, which we obtained from the homomorphism. So this is the utility of this theorem here. So I hope you understood these two examples well. Well, that is it for this video. Thank you for watching.